Okay, this is going to be Physics Chapter 5, Section 3. This one goes out to Lauren Dixon. Normally I don't announce grades over the air, but when you get 100 on a test, hey Lauren, way to go. Anyways, we're going to look at forces into dimensions. So we're going to be talking about equilibrium. Remember equilibrium, if the x and the y are all 0, then the thing's not moving. So we want to look at how we could find a force required for equilibrium, and also we're going to be doing this whole components thing where we break down vectors into components and see if we could resolve the force that way. So we're going to be talking about equilibrium. Again, equilibrium is when the net force on the object is 0. So you can use your skills by adding vectors to analyze a situation when the forces are not at 90-degree angles. We're going to remember that a net force is when the object is when the net force is 0, then the object is in equilibrium. If the object is in equilibrium, one of two things: it's either at a constant velocity or it's standing still. In other words, it's not accelerating or slowing down or turning or anything like that. In fact, it states here, remember that being at rest is a constant velocity. It just happens that that velocity is 0. So we're going to be looking at this equilibrium situation. It's important to realize that the equilibrium can occur no matter how many forces are acting on the object. You could have normal forces, you could have push-pull forces and everything, but as long as the object is not being moved, then we say that we have an equilibrium situation. We're going to look at a figure in a few minutes that has 3 forces, and we're going to see how we can figure out if there is a net force acting on it. To find the net force, we're going to add all the vectors together. Remember, the vectors can be moved. As long as you don't change their direction or their angle, you can move them around and we could add them up. So let's say we have these 3 vectors down here that are acting on it. We have force A off to the right and up. We have force B directly down and force C directly to the left, and we want to see if these 3 will add up to be to causing the object not to be moving at all. Well, if we start with force A, we put it there, and then we put the tail of B to the head of A and draw that, and then we put the tail of C to the head of B like that and draw that out, we'll find that we end up where we started. If we have a closed triangle, or we end up where we started, that means that there's no net force. It all balances out. So this is one way of doing this. We could also do it by doing the x's and the y's and adding up all the x's and y's and see if they all add up to 0. Okay, so suppose we have 2 forces that are exerting on an object, and they're not opposite each other, and the sum is not 0. One of two things. Either we have an object that's going to be accelerating, or we need to establish a third force that, when added to the other 2 forces, add up to 0 and therefore causes the object to be in equilibrium. If we're interested in equilibrium, then this has to be the case. To find the force, we first of all are going to add the 2 forces together. When we add those 2 forces together, we're going to get a single resultant force. And then if we come up with a force that's equal and opposite the resultant force, then we will restore equilibrium. So what does that look like? Okay, let's say we have force A and force B acting on an object. Now obviously the object would be pulled up in this upper left-hand direction. We can see that graphically by putting the tail of B over on the head of A and drawing it up, and then connecting those up, and we see a resultant R. If we don't balance out R, then R is going to cause the object to move up and to the left in that direction. But what we want is a vector that's equal to R but pointing in the opposite direction. If we put that in there, that's going to restore equilibrium and keep the object from accelerating in any particular direction. We call this an equilibriant. Okay. We're going to take another look at a situation. In this case, we're not going to have we're going to actually have a net force, and that net force is going to result in acceleration. This is a classic diagram that you see in just about every physics book. of a skier going down a slope. There's a couple of variations, but this is probably one of the most common ones. So let's take a look at the video and see what we got.
You have applied Newton's laws to a variety of equilibrium situations, but only to motions that were either horizontal or vertical. How would you apply them in a different situation? Say, a skier gliding down a slope. Let us start by identifying the forces acting on the skier and sketching a free body diagram as shown here. The gravitational force
Okay, here we are. That doesn't look right.
on the skier is in the downward direction
don't
toward
look
the
right at
center
all.
of Earth. There is a normal force perpendicular to the hill, and the frictional forces opposing the skier's motion are parallel to the hill. You get a free body diagram similar to this one.
Okay, again, I'm pausing just for a minute. You'll notice that they don't have the X horizontal and the Y vertical. They've tilted it so the X is parallel with the hill and the Y is supposed to be at 90 degrees to the hill. It's not quite 90, but if you kind of tilt your head, you could see it's at 90 degrees to the hill, or it's supposed to be 90 degrees to the hill. That makes it a lot easier because we're going to be looking at the acceleration down X. We have a normal force on Y, and we're going to take this force of gravity and divide it up into its X component, this direction, and its Y component. You'll see this in a second.
You can see that other than the force of friction, only one force acts horizontally or vertically, and you know from experience that the acceleration of the skier will be along the slope. How do you find the net force that causes the skier to accelerate? The force of gravity can be resolved into two components of force, one directed parallel to the inclined surface and the other directed perpendicular to the inclined surface. The perpendicular component of the force of gravity is directed opposite the normal force and balances the normal force. The parallel component of the force of gravity is not balanced by the frictional force present, which causes the skier to accelerate down the slope.
Okay, so that's the situation where we don't have an equilibrium established. We do have an acceleration, and like I said, this skier on the slope thing is a classic example of that. Remember that the Y force has to equal the normal force because the skier is not lifting up off the ramp. The skier is going down the ramp. So we're going to have a whole bunch of different ways we could attack this problem. Okay, once again, the inclined plane. Because the object's acceleration is usually parallel to the slope, one axis, usually the x-axis, should be in that direction. In other words, you need to tilt your coordinate system so that the x-axis is parallel with the slope. The y-axis is perpendicular to the slope. This coordinate system, there are two forces, a normal force and a friction force, and these forces are in the directions of the coordinated axis. The weight, again, is not. The weight is straight down towards the center of the Earth, and so that means that when the object is placed on the inclined plane, the magnitude of the normal force between the object and the plane is usually not equal to the weight. You'll need to apply Newton's laws to figure out in the x-axis and then again in the y-axis. Really kind of two separate problems. But keep in mind, if they're not moving up or down, then the y-axis should have a net force of 0. Because the weight does not point to either of these directions, you'll need to break this vector into its x component and its y component before you could sum these two forces. Okay, so that's it.